Welcome back to another video, and in this video we're going to look at something related to differentiation. Often this gets overlooked or it has a very small section in textbooks, but we're going to be looking at implicit differentiation. So at this point we've kind of looked at one thing with differentiation, and that was when y was equal to something. Now that something could be the square root of sine of x plus 1, that quantity squared. Y could equal 1 divided by x. Or y could equal a plethora of things, and we've looked at how to take the derivative of those functions. But what about functions that look like this, where we have x squared plus y squared equals 16? And sure, maybe you could say that y is equal to plus or minus the square root of 16 minus x squared. But what if you have a function that you can't really decouple like that? Let's say we have x times y squared plus x. Let's say that's equal to 3y to the fourth plus x squared. How do we take the derivative of that? Or what are we even taking the derivative of? And if we go back through history and look at implicit differentiation, we get brought to this folium of Descartes. I'm sure I'm pronouncing that awfully wrong. But we're going to consider this function, x cubed plus y cubed minus 3a times x times y, and that being equal to 0. So in this a is simply a constant. And from our little history lesson, we had Fermat, who said that he had a general method for finding slopes of tangent lines. Descartes said bet. And then ultimately Fermat did what Descartes couldn't, so he was able to differentiate this function and find that slope of a tangent line, which led to a good old mic drop, and now we have implicit differentiation. But aside from implicit differentiation, kind of just being used as a flex, we end up actually using it in thermodynamics, even economics. And recall that because the Earth is a donut, we can use Kepler's equations to figure out how the other planets actually orbit through the donut-shaped Earth. And then lastly, hysteresis, so we saw this in some of the previous courses. So that leads to this implicit differentiation being useful. And if we look at some general rules, so let's consider the function that we had above. And our rules are going to follow like this. We're going to have rule 1, and that's just establishing or realizing that y is a function of x, and we're going to differentiate that entire function with respect to x. And then when we do this differentiation, we're going to have to use the chain rule, maybe some other derivative tricks here, or maybe some algebra that we have to manipulate, which will lead us into rule number 4, or step number 4, and we're just going to solve for what that derivative of y with respect to x is equal to. Now sometimes this is easier said than done, so let's look at this equation and see what we do. So step 1 right here, we're just going to realize that y is a function of x. We could also realize that right here in the last term. Step 2, we're going to differentiate everything with respect to x. So we have the first term here, this second term here, and then this last term here. Notice here we differentiate the entire term, but because a is a constant and 3 is a constant, we're able to pull those out right here. And now we use our chain rule and other bag of tricks. So our chain rule is on that second term. We actually get to use the product rule on that last term, and that's going to again be equal to 0. And then with some algebraic manipulation, we arrive at step number 4. So we have this term, and notice here we were able to factor out dy dx, or that derivative of y with respect to x, and we can actually solve what that is. So in this case, this is what we're equal to, and this is our solution. Now if we want to consider plugging in some values, so let's say that a is equal to 2. Again, that a is just up here, it's a constant, and we want to know the tangent line at some point. That point is going to be 3, 3. So if we plug all of these values in to this equation right here, we get that the slope is equal to minus 1, and then recall our point slope form from some of the earlier videos in this course. So we just plug in the respected values, and what we get is that the equation for the line that's tangent at this point is equal to 6 minus x. But we can increase the complexity and look at another example. So again, we are going to use implicit differentiation to find the derivative with respect to x of this equation here. So step 1, realize that y is a function of x. So we just represent that like this. And then we do step 2, so derivative with respect to x. Notice in this term here on the left, we need to use the product rule, but also we need to use the chain rule because we have y squared as a function of x, and we want to take the derivative with respect to x. So we can just set up that left side of the equation like this. And then on the right side, we actually again have the chain rule, but now it's because we have something inside of this sine function here. And notice here, we did not do the chain rule for this derivative because that's what we're going to do in step 3. If you try to do everything at once, you might end up with some errors, especially if this is the first time you're seeing this, so that's why we have these rules. So we can carry through our chain rule, and we know that that's going to look something like this. Our right side doesn't change, because we don't need to do any chain rules, because we simply have dy dx right there. And then step 4 gets a little bit messy, because we want to do, again, that algebraic manipulation to have the derivative with respect to x, and then all those terms grouped together. And that's going to allow us to divide by this term to arrive at this result here. So we can say that the derivative with respect to x of y is equal to this. Again, looks a little bit more disgusting than what we saw up here, but because we followed the steps, we ended up at the correct result. And as always, if you learned anything new, found anything useful, please like, comment, share, subscribe. It helps the YouTube algorithm, and we'll see you in the next video. Thank you for watching.